Alright, you beautiful people. I know this has been quite the semester. Things are just freaking out of control. But, yeah, here are the answers. In case y'all are wondering, this is how I got them. So, I am 100% positive these are accurate and right, but, to each their own. I'm going to explain how I got them. So, the questions are, given the shaft shown, what is the minimum hole diameter that will always accept the shaft? Obviously, that's going to be the maximum limit of 24.04. Where do I get the 0.04? That would be this right here. This awesome thing right here. So the tolerance, right? So 24, diameter of this shaft is 24. It's plus or minus tolerance 0.04. So that just means the upper limit is going to be 24.04 and lower limit would be 23.96. Yeah. Now we're going to move on down to question B. If the minimum clearance between the shaft and a hole is equal to 0.02 and the tolerance on that hole is to be 0.6, what are the maximum minimum diameters for the hole? So you're going to take the maximum limit for the diameter for the shaft, right? 24.04. And you're going to add that to the minimum clearance, or the clearance of the hole, right? So that's going to be 0.02. And you're going to get 24.06. That is how the minimum limit the hole should be. Now the maximum limit that hole should be, you're going to take this minimum limit here, and you're going to add the tolerance of 0.6. So it should be 24.06. Oh, wait, no. Yeah, plus 0.6, and that should give you 24.66. And this is all in millimeters, in case you're wondering. But yeah, that's how you get it. Now on to the drawings and some slight explanation stuff, right? So I was having some technical difficulties, and I actually drew this stuff like 3 or 4 times. This is like my 4th time making this video, and the audio is finally working. Anyway, so you would start by making a 100 by 24 box, and then you're going to explode that box. So this is explode, in case you're wondering. You just highlight it all, and then explode it. And then from there, you're going to offset 3 on either direction. So you click offset, you type in 3, hit enter, and then you click this line and click over, and then click this line and click over, and then hit escape. So it's done. And then from here, you're going to click line and click on the corners and go down. You're going to hit tab at any real distance. It doesn't really matter as long as you're beyond this line right here. You hit tab, type in 45, and then hit enter. Or sorry, in this case it'd be like 135. And then the same for here, and then over here it'd be 45 on either side. And that's fine. And then I drew a line out from the center of this, so like this right here, like bam, that's center, and then I just took it out there and hit escape. So now you had a center point, so you click on circle, hit that, or not, sorry, diameter, and you just find your center point, which is like right in here, and then you move it out to 24, or you just type in 24 and it'll do that. And then you draw another line. Erase. So line. So you're going to draw a line out, just any random direction. You hit tab, hit 0, and you'll do that on both sides, this one and that one. And then what I did is I did annotate center mark, and you click that, so it gives you a center mark. So now you have intersection points of the lines that you would have. So you go back home, click on this, and you're going to hit the 2 point. So you would just click that point and this point, and that would be your circle. And now you're kind of caught up to where I'm at. So we don't need that stuff anymore. So here, we're going to draw a leader. So since we're at the home, under the home tab, right, annotation side, you can click the leader, and you're going to click wherever you want and just draw it out here. And then from there, you're going to click on symbols, click diameter, and then you're going to type in 24, and then click back symbol again, plus minus, and then you just put in 0.04 and just click out. And then how you do this, right? This is the major thing that everybody's kind of confused about. So click annotate. Let me see if there's one here. Nope. All right, so under the dimensions section in the annotate tab, click that drop down menu and you'll click right here. It's tolerance. So here are the symbols. These are all kinds of crazy symbols. I'll run through them real quick. So that's position. This is concentricity. Weird name, weird word. That one's not in the book. That's awesome. This one is parallelism. Perpendicularity. Jesus. Angularity. Cylindricity. That is flatness. That is circularity. This is straight, which is the one we need. This one is meant for like 3D stuff, but it's profile of the surface. This is a profile of a line. That one is circular run out, and this is total run out. But yeah, anyways, so that's it. So we're gonna go click on straightness. You can find that on page 479 in case you're curious. So what you'll do is you'll click this right here. This is the diameter symbol. And then you're going to type in 0.03 because that's what it is. All right, and material condition. So this is maximum material condition. This is at least material condition, and this is regardless of feature size. So that's cool, I guess. Yeah, some nerd decided this is how it is all going to go down, and so that's how it is. And by some nerd, I mean the American Society of Manufacturing, or no, not sorry, Mechanical Engineers. Yeah. Anyways, and then you just kind of click that underneath. That's awesome. Cool stuff. Next is go back to home. You just click on leader, and then you'll click wherever, take it up. And then you type in 3 space X45. And then you'll go up here to symbol again, click degrees. Then you're going to hit enter and both ends. All right, let's see. Boom. Cool. And you just click out. And so you have that all done. Super simple, super awesome. All right. So since that's all handy dandy and done now, oh yeah, and just make sure you put this little dimension in there too. That's super easy. You can do it with this. Just click that and then that point, bring it down, click, and you're done. All right. So yeah, that was a quick run through. So now you have the answers for that. I'm gonna do a little bit more. I'm gonna tell y'all why tolerancing is important. It's because I'm pretty sure that wasn't explained in class. I wasn't there, but I assume this is not something that it's been gone over. So AutoCAD, when you put something in here, it's perfect, right? So like this is perfectly however long it's supposed to be, the right amount. It's supposed to be 24 in diameter from this point to this point. In real life, unlike a computer system, nothing's ever perfect. So this is perfection, and in real life it isn't. So based off the material, so say you're going to cut in, say you have a 100 millimeter plate. That, just imagine this, but like it's just a square, right? So it's just like, say the plate is like that, right? If you flip it, if you flip it to the side and you zoom in, this would be like the width of that square we just made, right? So you're gonna take a hole saw and cut into it. Well, based off of how well this material is, like how it was manufactured to be that sheet metal that you're cutting into, like you could have a rough edge. Like it could be like a rough cut. You're always gonna have a rough cut, because the hole that's cutting this shaft out is literally another piece of metal, and it's just metal on metal grinding it out at a high rate of speed. So this is not a perfectly flat surface. So it's all going to be jagged and rough and just crazy, right? So that's where the tolerances stuff comes in. A bunch of nerds got together and founded the American Society of Mechanical Engineers. I'm sure somebody's crying about what I just said, but you know, it is what it is. I don't care. But yeah, and they made the standards for all of this stuff. Which is ASME standard Y14.5. That actually could be updated. I'm just going off of what I learned, but it's dimensioning and tolerancing, and it's basically the ASME standard. So that's where you get all of this stuff, the symbols, the tolerances, characteristics, and the terms. That those group of nerds got together and made it happen. So yeah, I mean that's pretty much what it comes down to it. And the reason tolerancing is so important, it allows you to be like 100% certain that your part is going to fit and function properly when everything's assembled. So imagine this is wood and you're building a shelf, right? So this is going to fit, like you're trying, like down here, this right here is trying to find the minimum limit for the holes. So how much those holes have to be. So like when you have your shelf, right? You need to make sure this shaft, let's say it's like a little dowel rod or whatever, is to hold the shelf in place, fits inside of that hole. Like I'm sure most of you have built something that is similar to that, right? So tolerances gives you like a plus and minus, like lateral limits to what it needs to be to where everything fits together properly. And the reason that's so important is because you're gonna have to, it greatly reduces fitment tests, and it's gonna save time and money in a manufacturing process. Uh, so if you create tolerance limits in advance, like before moving into the actual process, it eliminates a lot of the guesswork, and it's going to reduce waste. So a lot of us have taken the Lean Six Sigma course by now, and yeah, so you're always trying to reduce waste and increase proficiency and efficiency. Um, so you make it like a continuous process, and if you're just doing the basic guesswork and like trial and error, you're gonna be literally making making a shaft or cutting a hole and trying to fit that shaft in that hole and be like, oh, it doesn't fit. So you go back to them. So it'd be like your design phase, right? So you design something like this, and you send it to the machine shop for them to machine it and fix and make it. So from there, it's going to move down to your inspection department, which is your quality engineers. They're going to try and put stuff together and be like, oh, yo, this shaft's too big for this hole, or yo, this hole's too small for this shaft. Either or. So then it gets sent back to the machine shop, and they got to redo it. So it's like trial and error is not efficient at all, because that's gonna cost you time and money. Those are two major things that any business wants to be successful. You always got to make the most out of your time and money. So that's why tolerances are very important. if you're wondering like, why would you accept a less tolerant part, yeah, answer goes back to time and money. Because if you're constantly focused on trying to make this perfect, like an exact diameter 24, I mean, you're gonna obviously take more time. You're gonna have to get more, like higher end, like precision instruments and precision style equipment, and then you're gonna have higher wait times because you're trying to get that perfect amount, right? And nobody likes that. Nobody wants to do that. No company is gonna like if you have the best product in the world, but it takes you 3 years to produce one. That it may be the best in the world, but it's not gonna last long because somebody will make something slightly better than or slightly less good than that. For insert the proper term for that, and shell them out like 3, 4 times as fast, and they're gonna take your all of your business, and your business is gonna go bankrupt. So that's the whole reason behind it. Why tolerances are so important, so you can make it as efficient as possible. And I mean, there are some things that require a very high degree of precision, like aerospace, circuit cards, uh, motherboards, like anything cute. Most computer related things like motherboards, nanotechnology stuff, like all that's very important. So obviously it takes longer to build, takes a lot more resources, and if you mess one thing up, you gotta scrap it and do it all over again. Like it's tedious, but those things obviously are very niche. But in any normal manufacturing line, you're trying to reduce costs and shell out as many as possible. So yeah, that's the whole reason behind tolerances and why they're so important. That's the nitty and gritty. I mean, I could probably explain it a lot better given more time, but yeah, that's pretty much it. If y'all have any questions, just reach out and I'll be able to answer them to the best of my ability. I don't know. Let's finish strong. You guys got this.